Where we are. This should look familiar. We talked about this idea of vapor pressure, which is the pressure of a gas in a closed container that is in equilibrium with its liquid. We talked about the idea that vapor pressure is a function of temperature. So the higher the temperature, the higher the vapor pressure. We also talked about the idea that vapor pressure is a function of intermolecular force. So if you have two dissimilar liquids, the liquid that has the higher intermolecular forces will have the lower vapor pressure. Make sure that jives, y'all. Higher intermolecular forces, lower vapor pressure, because the molecules are more stuck together and less likely to be in the vapor phase. Then, guys, we connected that to volatility and boiling point, which are things we talked about last year. So if you have a liquid with a low vapor pressure, it will also have a low volatility because it doesn't evaporate very readily, and it will have a higher boiling point because it's harder to break apart and it boils at a higher temperature. Anything you need to talk about? You guys good? Okay. So guys, this then becomes the transition. So we've been talking about solids, we've been talking about liquids, we've been talking about gases. Guys, today what we're going to do to wrap up the day is we're going to look at these things called phase diagrams. So in a minute, I'm going to ask you to draw this because they will ask you to draw these in free response on the AP test. In multiple choice, they'll have you interpret them, but I have seen in free response where they've asked you to sketch them. So with that said, guys, don't write any of this down yet, but fundamentally, what is a phase diagram? Well, guys, let me zoom into this and let's talk about what they are. So obviously it's a graph or something that resembles a graph. And obviously it's got three regions, as you might be picking up, because this is a phase diagram and because there are three phases. Guys, those three phases are represented on the graph. So we've got solids, liquids, and gases. One of these regions is solid, one is liquid, and one is gas. So before we get into the details, let's look at this, figure out how it's organized, and then figure out which is which. So guys, first of all, you'll notice the axes. The x-axis is temperature, the y-axis is pressure, and the origin is 0 on both axes. You guys know about the origin of a graph, right? So let's talk about it. So guys, if that's the case, tell me about the conditions right here. It's a vacuum at absolute 0. Does that make sense? This is 0 pressure, which is a perfect vacuum, and 0 Kelvin, although we know theoretically, we've never been there in theory. So this is 0 kinetic energy, 0 Kelvin, and it's 0 pressure, so very, very low pressures. Is that okay? Okay. So guys, with that said then, let's talk about what the different phases are. So let's first of all talk about this. What is this phase going to be? Solid, liquid, or gas? How do you know? High temperature, right? When you're at high temperatures, these substances will most likely be gases. Does that make sense? Okay. So then guys, let's look at the other extreme. What then does that make this area? The solids, and then of course the liquids are in between. They're like an intermediate phase. So guys, because that's the case, then we can talk about the lines. Sorry, I should have been better prepared. Just a second. We can then talk about the lines that separate these phases. And so let me grab some writing stuff. So guys, when we look at these lines then, oh, my board shut off. Hold on. So when we look at the lines then that separate the phases, guys, what does this line right here represent? Melting, or if we're going in this direction, so this way would be melting, this way would be freezing, right? And then this would be boiling, and this would be condensation, and this would be sublimation, and then do you remember this one? Deposition, right? So all of the phases are represented on this graph, on this chart. So then, guys, what about that point right there? That point is what is called the triple point. Guys, what is true at the triple point? All three phases are in equilibrium. So guys, the question then becomes, what would that look like? And by the way, this is actually the phase diagram for water. This is what it looks like. We'll talk more about that in a minute. So guys, the question becomes, what would it look like if you had water at its triple point? What would it look like? Yeah, it would look like a glass of ice water. It's really not much to look at. Guys, it looks like this. It is literally a glass of ice water with a lid on it. Why do we need a lid? Because that controls pressure. So it literally looks like this. So what's so magic about this if it looks like a cup of ice water? The thing that's magic about it is if you come back a day later, guess what it still looks like? That. And it never changes. Guys, that's the thing that's interesting about this. And now you're going, well, wait, yeah, I can take a cup of ice water, and if I hold it at 0 Celsius, it'll never melt or freeze. The difference is that in this case, nor will it sublimate or deposit. So you literally have vaporization, condensation, sublimation, deposition, melting, and freezing all happening simultaneously. And it never changes. It will always be this. Yeah.
So, like according to the diagram,
yeah.
it happens at a certain temperature and pressure.
Good.
But could we do that at different temperatures and pressures?
No. So, but what you're saying is correct. This point only exists at one combination of temperature and pressure. So for different substances, they're different, but if we're talking specifically about water, there's only one temperature-pressure combination where that happens. Exactly. It has to be exactly at this temperature and pressure. And I'll show you, we'll put numbers to it in a minute. This is right around 0 degrees Celsius. It's either a hair above or a hair below. I don't remember. The thing that makes it exotic is how low the pressure has to be. The triple point of water is at such a low pressure that we don't have a vacuum pump good enough to get there here. You can Google it and you'll see videos of water at the triple point, and frankly they're boring because nothing changes. But you need a really good vacuum pump to get there. So, and I'll show you pictures. So guys, and then we should talk about this. What then does that represent? The boiling or the condensation point. And so guys, interestingly, if this is 1 atmosphere of pressure, what would that temperature be? 100 degrees Celsius. And you can start to make those connections. Then guys, finally up here, we need to talk about this thing called the critical point. These are the points the parts that you need to know. So guys, what do you notice about what happens in this graph? Let me erase, just to get the mess out of the way. So guys, up here at this thing that's called the triple point, what do you notice? The line stops. Guys, the critical point, not the triple point, the critical point. Guys, the critical point is this magic high pressure, high temperature system at which liquids and gases become, and forgive me if I can't use this word, but guys, liquids and gases become indistinguishable. You can't tell the difference. So beyond this critical point, you get what is called a supercritical fluid. It is another phase of matter. You've got solids, you've got liquids, you've got gases. There's actually another phase of matter. And basically the way to think about it is so ridiculously hot that the liquid would like to boil, but the pressure is so ridiculously high that it can't. And we're talking very, very exotic temperature and pressure conditions. But there is another phase of matter called a supercritical fluid. And this phase of matter actually takes on the characteristic properties of a liquid and a gas simultaneously. It's hard to picture, but it happens. Go ahead. We'll look it up and it'll show you in a second. But guys, please understand, I know this seems like science fiction, right? But understand, guys, supercritical fluids actually do have industrial uses. The one that the book mentions, if you happen to read this, is they actually make decaffeinated coffee beans by soaking them in supercritical carbon dioxide. It turns out that supercritical CO2 is a great solvent for caffeine. It doesn't dissolve the oils in coffee, because it's the oils that give coffee its flavor. But if you don't want the caffeine, you need a solvent that dissolves caffeine but doesn't dissolve the oils that give it its flavor. And they use supercritical carbon dioxide. So they literally take the coffee beans after they're roasted and they soak them in supercritical carbon dioxide, and that actually dissolves the caffeine. They draw off the solution, the caffeine's gone, and you're left with decaffeinated coffee beans. So this stuff is exotic, but it does actually exist and has some commercial uses. So you get the idea? And that's in the book if you want to read more about it. So you guys good on this? So what I want to do is, rather than talk with you more about this, I want to let the video that came with our book sort of give this a shot. So they're going to talk with you not only about the regions and the triple point and the critical point, they're also going to talk with you about how to interpret changes in these graphs. What happens when pressure goes up? What happens when temperature goes up? And guys, these are the kind of things you're going to see on the AP test. So we're going to spend some time with it and make sure that it makes sense. So the volume could be wacky. So let's check and then we'll come back.
The phases exist in equilibrium with one another. For
okay?
example, in the phase...
So starting again then. Here we go. So we'll watch it through once and then we'll come back and pick it apart.
A phase diagram indicates the temperature and pressure conditions under which a substance is a solid, a liquid, or a gas. The lines that separate the phases are called phase boundaries. At any point along a phase boundary, the phases exist in equilibrium with one another. For example, in the phase diagram of water, at 1 atmosphere of pressure and 100 degrees Celsius, liquid water and water vapor exist in equilibrium. This point is known as the normal boiling point of water. Likewise, the temperature at which solid and liquid water are in equilibrium at 1 atmosphere of pressure is known as the normal melting point. The point at which all three phase boundaries come together is known as the triple point.
Sorry, I do want to stop it here. So yeah, guys, check out these conditions for the triple point of water. So it's 98 tens, hundreds, thousands. So 98 10,000ths of a degree above freezing. Not absolute zero. This is in Celsius. So, I mean, it is colder than that right now outside, right? Because it's below 32. 32 is 0 Celsius. So we're actually below this temperature right now. The crazy part is the 4.5 torr. What's standard pressure in torr? 760, right? So this is darn near a perfect vacuum. We don't have a pump good enough to do that.
So it's 0 torr.
Say that again.
So 0 torr.
Yes, yeah. So 0 torr, 0 pressure would be a perfect vacuum.
This corresponds to the temperature and pressure combination at which all three phases of a substance exist simultaneously in equilibrium.
Here's where they then start talking about changes. And guys, you will see questions like this in multiple choice on the AP test and our test.
If a sample of solid water or ice at 1 atmosphere of pressure is heated, it will melt when the normal melting point, 0 degrees Celsius, is reached. At this point, water crosses the solid-liquid phase boundary. If the sample is heated further, the liquid water's temperature will increase until it reaches the normal boiling point, 100 degrees Celsius. It will then vaporize, crossing the liquid-gas phase boundary.
And guys, did you pick up on the idea that normal simply means at 1 atmosphere of pressure?
Once the liquid is all vaporized, the temperature of the water vapor will increase as more heat is added. If a sample of solid water is heated at a pressure below the triple point,
So guys, now what we're going to do is we're going to take a solid and we're going to heat it up at a pressure below the triple point. But remember where the triple point pressure is. 4.5 torr, right? So this is clearly not something that happens here on Earth.
it will sublime rather than melt as the temperature increases, because the only phase boundary it will cross is that between the solid and vapor phases. We can also track the changes in a sample of water as we vary pressure. If the pressure is increased on a sample of water vapor at 110 degrees Celsius,
So guys, what's going to happen? If you take water vapor and squeeze it, so the temperature stays 110, but if you squeeze it, eventually what is it going to do? It's going to liquefy.
will condense as it crosses the gas-liquid phase boundary.
This one's interesting. So now we're at a temperature that is slightly above the freezing point of water. I'm sorry, slightly below. So we're at 0.5 Celsius. So water is ice. It's a solid, slightly below the freezing point of water. The question is, what happens if we increase the pressure? What's going to happen? Which direction will this dot move if we increase pressure? Up, down, left, or right? Up. And eventually what's going to happen? It's going to melt.
Note that a sample of solid water or ice at a temperature slightly below the normal melting point will cross the solid-liquid phase boundary and melt as pressure is increased. This is one of water's unusual properties.
So guys, I like the way they said that. This is one of water's unusual properties. So let's talk about it. So this is ice, right? And what we just demonstrated is if we, oh, I lost the line. I just paused a little too late. So guys, if we take this ice at negative 0.5 degrees Celsius, and if we squeeze it and the pressure goes up, eventually it melts. Why is that true? Go ahead. Exactly. Guys, ice is less dense than liquid water. And here on Earth, it's the only substance for which that is the case. There are two other substances that are these really like exotic salts. But guys, for all intensive purposes, water is the only substance on Earth that expands when it freezes, right? That's why our pipes burst when they freeze. Guys, understand that if our pipes in our home were full of any other liquid but water, they would never burst, because any other liquid contracts when it freezes and it would get smaller. The frozen form would be smaller and our pipes wouldn't burst. Guys, water is the only substance on Earth, except for those other two weird ones, that it expands when it freezes. But you understand what that means. Water is the only substance that it's solid, floats in its liquid. So we're accustomed to having a glass of ice water and the ice floats, right? If you had a cup of any other liquid with its solid in it, the solid would be on the bottom. Some of you have done this. Have you ever melted wax to do canning? Yeah, and if you've got a saucepan of liquid wax, and if you add another cube of wax to the saucepan, where does the cube go? To the bottom. Guys, water is the only substance that expands and becomes less dense when it freezes. So now use the logic. If water expands when it freezes, if you squeeze it, what does that make it want to do? Melt. And that you can see here, that as you take this solid ice and you squeeze it, it actually makes it harder to be a solid, and eventually you can squeeze it hard enough that it melts and becomes a liquid. You understand this is how ice skates work. Guys, when you ice skate, you are actually not skating on a sheet of ice. The pressure of your weight concentrated on that skate blade squishes the ice and makes it melt. So you are actually gliding on a very thin sheet of water that's on top of the ice. And eventually that becomes a big enough problem because people have skated all over the ice, and now you got to bring out the Zamboni and refreeze it, because you end up with all of these little water grooves all throughout the ice. Huh? Go ahead, Levi. Oh, okay, go ahead. Mm-hmm. No, it's because when you grab ice and hold on to it, the reason that that's melting is because you'd have to squeeze it. I don't know that any of us is strong enough to squeeze the ice hard enough to get it to melt. Yeah, no, the reason that happens is because you're adding heat. Yeah.
So last time you were talking about how you were about to...
Yeah, and it sublimates. As I was saying that out loud, I was realizing we may need to talk about this. So remember we talked about the idea that many times the snow up on temp does sublimate. You're right, we should explain it. The reason that happens is because of wind. That actually, as wind travels across the ice, it can actually pick up those water molecules in the frozen state and move them out. So it's not technically sublimation in the same sense we're talking about here. It's an atmospheric phenomenon. We still call it sublimation because it never gets wet. It goes from the solid to the gas form, but it's the movement of the air across the snow surface that allows it to happen. So it's a little more complicated than just what we're saying here. So you guys good on the idea? So now let me ask you a question. This is deep. You ready? So this represents the phase diagram for water, right? And we now understand that water is unique because water, and we're just going to say the only, we know there are a couple exceptions, but guys, water is the only substance that expands when it freezes. Therefore, increasing pressure causes it to melt. But if water is the only substance that does this, then water should then also be the only substance that has a phase diagram that looks like this. So then the question becomes, what does the phase diagram for every other substance on the planet look like? How will it be different? Go ahead. It's going to be slanted the other way. So guys, for every other substance, this line slants this way, and this is... you get the idea. This is solid over here. So the idea is if you've got a liquid here and you squeeze it, it becomes a solid, right? Doesn't that make sense? If any other substance becomes more dense when it freezes, every other substance on the planet at any given temperature, if you squeeze it, the pressure goes up and eventually it will solidify, not melt. So that's exactly the idea. For every other substance on Earth, this phase boundary between solid and liquid has a positive rather than a negative slope. Just a second. Go ahead, Jessica. Say that again. It's not easier. I mean, perhaps it's more likely, but... I don't, forgive me, but I don't even know if that's a question worth pursuing, simply because the answer to that question is different for every substance, and it depends upon the particular environmental conditions. So I would be careful about chasing that too far. Yeah, no, I mean, it seems reasonable, right? Because this is smaller than this is smaller than this. But the thing that you have to keep in mind is that life, if you will, happens in that that's not quite. So the temperatures and pressures that we experience here on Earth are a very small fraction of the entire diagram. And at that point, these kind of have very similar areas. Does that make sense? It has to be exotic conditions that certainly don't exist here on Earth. So, yeah. Yeah. Go ahead, Lit.
So does that mean that also water is going to be the only substance that you can apply as much pressure as you want to a liquid and it will never solidify? Right?
Hold on, I got to think about that. So is water the only substance that you can impress? Yes.
On all the other substances, the light goes.
Yeah, right. Yeah, because I mean, this is not bounded, right? This continues on, and if that continues on, and if this continues up, that distance, that temperature change, if you will, is ever increasing. So absolutely. So the more you squeeze, the even more you've got to cool to get it to solidify. Yeah. So what you're saying is true. Go ahead.
So if we were to like, expand the graph,
Yeah.
would eventually the supercritical fluid like creep over all the way over?
No, it's here. So I see what you're saying. Would this go that? I have no idea. So would the supercritical fluid eventually become a solid? I don't know. I'm not sure. Yeah, I have no idea. What if we said yes? And then you could do a science fair project and try to find it. There you go. So yes, actually. Good. You guys okay? So let's continue to let this play. Oh no. Or let's switch slides.
On a sample of water vapor at 110 degrees Celsius, it will condense as it crosses the gas-liquid phase boundary.
And guys, maybe we should talk about this. I don't know if this is familiar enough to you as it should be. You understand this idea that we can take gases and we can cause them to liquefy, not just by cooling them. Certainly we can do that. We can take a gas, and if we cool it down, it'll eventually condense. But we can also take a gas and we can liquefy it, not by decreasing temperature, but by increasing pressure. Yeah? And guys, if you're not sure what I'm talking about, that's what's inside here. This is literally liquid air. And you pull the trigger and the air comes out. But guys, if you can hear this slosh, can you hear it slosh? Guys, this is liquid air. Literally inside here, they just take air and they turn it into a liquid. The question is, how do they do that? Well, they don't do that by taking air, which is a gas, and cooling it down. This isn't cold. So how do they get the air to turn into a liquid? They increase the pressure. This is under, I think it's like 5 or 6 atmospheres of pressure. You can look it up. But guys, because this is under such pressure, the gas is so compressed that the intermolecular forces that exist even between nonpolar gas molecules, induced dipoles, right? Even those seemingly nonpolar molecules, if you can push them close enough together, their induced dipoles become important enough that they liquefy. And so literally this is full of liquid air and you can hear it slosh around. Go ahead, Mark.
So when we heat up, or when we cool down our gas,
Mm-hmm.
liquid,
Uh-huh.
and when it does the phase change,
Mhm.
like, sure,
Correct.
does this
Right.
thing happen with pressures like
Mhm.
it's increasing?
Absolutely. I understand it's a little bit different. So let me zoom out so I can get in writing mode. So Mark's question is, what if we could track not temperature and pressure, but what if we could track energy and temperature? And so, is this okay? Can I stay this zoomed out? Can you see okay? So the question is, if just disregard everything that's on there, but the idea is if we take a liquid and if we heat it up and we turn it into a gas, we understand that as we heat the liquid, the temperature goes up, and then when it boils, the temperature stops changing. So this stop changing temperature happens at this boundary. And what's happening at that point is that the intermolecular forces are breaking. So as we cross this point, the addition of energy that causes a temperature change no longer causes a temperature change, because the thing that's changing at that point is intermolecular forces are falling apart. Similarly, if we go the other direction, and if we take you went this way, if we take a gas and if we squeeze it, it still crosses that boundary, right? And so what's happening is the intermolecular forces are forming. And as that happens, the temperature doesn't change. But understand that when we're changing pressure, we're not changing temperature simultaneously. What we are doing is work. because remember, there's two ways to change the energy of a system: heat. And when we change heat, we're looking at this axis. When we change energy relative to this axis, that's a function of work. And so at that point, we don't talk about temperature because temperature is not changing anyway. But what would happen is as we're doing work, the amount of work that we would have to put in, the amount of work that we have to put in changes at that point, because we're no longer doing work to get the molecules closer together. We're doing work to cause the intermolecular forces to form, which is a different amount of work. So it's a different idea, and thankfully we don't have to talk about that in this class. So yeah. Yeah, but it always changes. It weakens and strengthens based upon temperature. Eventually it becomes weak enough that it breaks. So, I mean, we can approximate intermolecular forces computationally based upon the structure of the molecule and the electronegativities of the atoms. But how that, so in that sense we can measure polarity. How that plays out relative to intermolecular forces is dependent upon so many other factors. But if you can control those factors, if you say at this temperature, this pressure, and this density, then yeah, we can figure out the strength of the IMFs. Yeah. You guys good? Okay, so let's let this continue. Oh, go ahead, Levi. With what? Oh, yeah.
Why does it work more than once? Because if you squeeze it with the pressure, it's not down.
Because it's a small hole. So as this happens, I mean, let me turn the question to you another way. Why is it when you boil a cup of water, all the water doesn't come out at once? Because that's really what's going on inside here. Is there's literally the liquid is at the bottom, and when we open this up, it's boiling. Literally, this liquid is now boiling at room temperature because the pressure is changing. It's now boiling. And just like water boils progressively from the top, so does this liquid air, and it boils progressively from the top. Because those molecules have got to get to the surface before they can escape, and all the other molecules are just waiting their turn. Now understand that would be different than if I took this thing outside and shot it with a gun. If I could get this can to fail wholesale all at once, then all of it would boil all at once, because it all has access to a surface and it just goes. Is that okay? Yeah?
Is that why CO2 canisters, when I let
expansion of gases? Because you're right, that if you do this, I'm going to throw this to you. You ready? It's cold, right? Yeah, so as we allow that gas to escape, it gets cold. So let's talk about why. So what did it take to get the gas to go in here? And the answer is work. They literally take a pump and they pump the gas into the container. So the energy of the gas is greater because it had work done on it to get it to fit into the can. Well, now the opposite is true. When it escapes the can, the energy that was originally added to it as it went in is now being released, if you will. But now instead of being released in the form of work, it's being released in the form of heat, and it makes this cold. And it is called the thermal expansion of gases. So anytime you have a gas that goes from a small size to a large size, especially if it's going through a phase change as it boils, you'll experience it as being cold. You may have seen this, like if you have a propane barbecue grill, and if you, even in the summer, if you run your grill long enough, you can actually see that the propane tank even will get frosty because the gas cools down and the humidity in the air condenses to it, and you'll actually get even frost on the side of a propane tank. It's actually another way you can tell how much propane you have in your tank. Run your grill for a while, and if you let your hands run up the side of the propane tank where it feels cold, that's where the liquid is, and you'll feel the temperature change, and the change in temperature indicates the surface of the liquid. So, yeah, we're learning so much today. You guys good? We doing okay? So have you guys ever seen those tank indicators on propane tanks where it's like a strip that's stuck to the side of the propane tank? All that is a thermometer, and it's actually sensing the temperature. Anyway. Come on. Oh, I'm drawing dots. All right, so let's keep going. Oh, this is the awkward pause.
Note that a sample of solid water or ice at a temperature slightly below the normal melting point will cross the solid-liquid phase boundary and melt as pressure is increased. This is one of water's unusual properties.
That's where we got to before.
The critical temperature is the temperature above which a gas cannot be liquefied regardless of the amount of pressure applied.
So there's the critical temperature for water, 375 Celsius, so almost 4 times boiling. That's Celsius.
The critical pressure is the pressure necessary.
217, that's not torr, that's atmospheres. So if you want it in torr, multiply 217 times 760.
To liquefy a gas at the critical temperature. The critical point is defined by the critical temperature and the critical pressure. Note that there is no phase boundary beyond the critical point. A substance in this region is known as a supercritical fluid and has properties associated with both gases and liquids.
You guys okay? Okay, go ahead.
So like a steam room where it's like water, steam,
Yeah.
turns into liquid right on the walls.
Yeah, yeah.
Just like, because it's close, or not much there.
Well, yeah, so, I mean, we can track that on here. So you've got steam, right, in a steam room, but then the question is, why does it drip down the walls? So the walls are cooler than the steam. And so when the steam molecules hit the wall, they lose energy to the wall. And as they lose energy to the wall, they cross through that phase boundary and they liquefy. So, yeah, and it's all because they're losing heat to the walls. Yeah. You guys good? Okay. So, guys, there is one more thing, if I can stop drawing dots, that I want to show you. And that would be this. So, guys, comparing the two, this is, again, the phase diagram for water. Notice that we've got the critical point, the triple point labeled, we've got the critical point labeled, and so on. Guys, the one on the right is actually the phase diagram for carbon dioxide. And there are some interesting things to notice. First of all, down here is standard conditions. 1 atmosphere of pressure. Do you now understand why we call carbon dioxide dry ice? See, guys, look. The triple point of carbon dioxide is 5 times standard atmospheric pressure. So where we live at 1 atmosphere of pressure, carbon dioxide cannot be a liquid. So if standard pressure is below the critical point pressure, then whatever that substance is can't exist as a liquid. As a result, when you heat dry ice, it goes straight from the liquid to the gas form, and it never passes through the liquid form because that triple point is above the pressure that we experience here on Earth. Yeah.
So, like, same thing we were saying with the steam room, if you could cool something down to, like, below 78.5 degrees Celsius, would the carbon dioxide, like, solidify on it?
Yes. At this pressure, yes, absolutely, yeah. Yeah, so if you could cool whatever that thing is down to below this temperature, then you would get carbon dioxide crystallizing on that surface. Yeah, absolutely. But then, guys, also notice this, and Doug mentioned it first, but guys, notice the slope of this line. It's positive and not negative, meaning that if you did take liquid carbon dioxide and squeeze it, it would freeze, it would not melt. And every other substance on Earth other than water has a positive slope to that boundary, and therefore it goes in that direction. You okay? Yep. Okay. So, guys, with all of that said, there is one more thing that we need to address, and it's all about solids. This is this is in 12.1 and 12.2. Don't read anything more, but do read those. You're going to run into the idea of crystalline solids. You're going to run into the idea of amorphous solids. Then, under the heading of crystalline solids, you're going to find out that there are 4 types. There are molecular solids, there are covalent network solids, there are ionic solids, and they are metallic solids. Now guys, as you interact with this material, and we're not going to look at this extensively now, we'll talk about it more next time. Guys, when you think molecular solids, think sugar. When you think covalent network solids, got it. Think diamond. And guys, when you think ionic solids, think salt. And when you think metallic solids, think aluminum or steel or whatever you think of. So guys, you need to be able to differentiate these things. Look at the homework questions relative to this, and then guys, we will be able to cover this material at the depth that we need to when we grade homework on Friday. So we're not, read 12.1 and 12.2. There isn't, and then we'll talk. Okay? So guys, with that said, this is, and this will be in the screencast if you need it. It's all there. So with that said, guys, let's get, no, I'm going to keep that. Let me